Imagine walking into like a massive, highly secure office building where you never once have to pull out an ID badge or a passport or a key card.
Right, you just walk right in.
Yeah, you just walk up to a restricted door on the 50th floor, and the room itself mathematically knows exactly who you are, what files you're allowed to see, and what your specific preferences are. The building just handles your context invisibly and perfectly.
Which, I mean, it sounds like science fiction, especially if you've ever tried to navigate a real corporate security system.
Oh, absolutely.
But in the architecture of complex software, figuring out how to manage that kind of invisible perfect context is a very real and honestly very difficult engineering problem.
And that exact problem is what we are dissecting today. So welcome to the deep dive. Our mission today is to take, a highly technical, seemingly microscopic entry from a developer's journal and kind of unpack it.
To reveal a massive concept about how complex systems are actually managed.
Exactly. Our source material is a blog post by a developer named Eng. It's dated August 18th, 2026, and it's titled Notes-on-Haskell-Programming, Part 216.
Which is a title that might make anyone who isn't a software engineer immediately brace for impact. I mean, Haskell has a reputation.
A pretty intimidating one.
Yeah. It is a strictly functional, highly mathematical programming language. It's not exactly known for being casual weekend reading.
No, it's really not. But that is exactly why we are diving into it. Because you don't need to be a Haskell programmer to grasp what Eng is doing here.
Right.
Even if you have never written a single line of code, this deep dive is going to reveal the underlying mechanics of how developers organize, pure chaos.
We're going to be looking at one specific code refactoring. Eng is taking a function called printContent and moving it into something called an app monad.
Right, representing a fundamental shift from what Eng calls explicit manual dependency injection to implicit auto-dependency injection.
Yeah. And we are really going to look closely at the mechanics of why that shift is so necessary. Like, we're not just going to list what the code does.
Yeah, nobody wants that.
Right. We are going to explore the philosophy behind it. Why certain approaches cause systems to literally collapse under their own weight, and how a concept like a custom monad actually functions in practice to keep software reliable.
Uncrashable, even. We want to upgrade your mental model of how information flows, whether you're organizing a massive digital server farm, managing a supply chain, or honestly, just trying to get different departments in your company to talk to each other without losing data.
The principles of context management apply everywhere.
They really do. So, okay, let's unpack this. To appreciate Eng's solution, we have to start with a pain point. We need to look at the before state of this printContent function.
Because in software engineering, you rarely invent a complex architectural pattern unless the simpler way has just become utterly unbearable.
Right.
And the unbearable problem here is how configuration data was being forced through the system.
Yeah, so Eng gives us the old function signature in the post. And a function signature is basically the contract that tells you what inputs a function requires and what output it produces.
Exactly.
So the old signature looked like this: handle, verbosity, pandoc, and then IO. Now, to understand the headache here, we really need to translate those terms.
Let's break those down. A handle is essentially a pointer to where the output should go.
Like telling the program to write to a specific file or print to the screen.
Right. And then verbosity is a configuration setting. It just tells the program how detailed its log should be.
Like, do you want every tiny detail logged or just the critical errors?
Exactly. Then we have pandoc, which is the actual data being processed. It's a widely used tool for converting documents from one format to another.
Like turning a markdown file into an HTML web page, things like that.
Yeah. And finally, the output is IO, which means this function performs an input-output action. It interacts with the messy real world, like writing a file to a hard drive, but it doesn't return any new calculation back to the program.
Okay, so when you look at that signature, handle, verbosity, and pandoc are all being explicitly handed to the printContent function.
Yes. Eng was passing these configuration parameters things grouped under the overarching term arguments explicitly down the line.
And on a small scale, I mean, that seems perfectly reasonable. Like, if a function needs to know how loud to make the logs, you just hand it the verbosity setting.
Sure.
But Eng describes this explicit manual dependency injection as a major problem. So why does passing a few arguments cause a system to break down?
Well, mostly because of the sheer depth of modern software. In functional programming languages like Haskell, functions are meant to be pure.
Meaning what, exactly?
Well, unlike object-oriented languages like Python or Java,
Yeah.
where you might have an object that just internally stores its own state, functional programming requires you to pass the data a function needs directly into it.
Oh, I see. So if a function is nested deep inside a program, it can't just like reach out and check a global setting. It literally has to be handed that setting.
Exactly. Imagine a stack of functions, 10 layers deep. Function A calls function B, which calls function C, all the way down to function J.
Right.
Now, let's say function J at the very bottom is our printContent function. It needs that verbosity setting to know how to log its actions.
Okay.
In the explicit manual approach, function A has to take the verbosity setting and hand it to B. B hands it to C, C to D, and so on, all the way to J.
Wow. Okay. Going back to the office building analogy, that sounds like making an employee carry their birth certificate, a passport, and a utility bill every single time they walk through a different internal door.
That's a perfect way to picture it.
I mean, the doors in the middle don't even care about the utility bill. They just have to act as couriers to get the document to the security desk on the top floor.
And that courier duty fundamentally breaks a core principle of software design, which is the separation of concerns.
Because the middle doors are doing jobs they shouldn't be doing.
Right. Those intermediate functions shouldn't have to know that verbosity even exists. They have their own logic to execute. But because they're forced to act as a bucket brigade for this configuration data, the code gets incredibly noisy.
So you end up with function signatures that are cluttered with arguments they don't actually use. They just like pass them along.
Exactly, which makes the whole system rigid.
I can imagine. Because if I decide tomorrow that function J also needs a database password, I can't just give it directly to function J.
Nope.
I have to go back and rewrite the function signatures for A, B, C, D, E, F, G, H, and I, just so they can pass the new password down the chain.
Which is tedious, it's highly prone to human error, and it frankly makes refactoring your code a nightmare. Every time you change the config requirements at the bottom of the stack, a shockwave of necessary updates just ripples all the way to the top.
That sounds miserable. So that is the pain point of explicit dependency injection.
Big time.
So if manual courier duty paralyzes the system, how do you get this configuration data to the bottom layer without passing it through all the middle layers?
Well, this is where Aang introduces a custom wrapper called the app monad.
Right. In the journal, the new function signature goes from that long, clunky string of arguments down to literally just this, pandoc to app.
It's so much cleaner.
It only takes the document it needs to process, and it outputs this app action. The handle and the verbosity are completely gone from the signature.
They're gone from the signature, yeah, but they aren't gone from the program. They've just been abstracted away into that app wrapper.
Okay, here's where it gets really interesting. But I feel like I need to stop right here and clarify what a monad actually is, because it's a notoriously intimidating term in computer science.
Oh, absolutely. It scares a lot of people off.
Yeah. Aang explains that this app monad is a wrapper over the standard I/O monad. But what exactly is a monad doing in, plain English?
In the simplest terms, a monad is a protective container. It provides a specific context for the code running inside of it. Let's look at the standard I/O monad first. Haskell is obsessed with purity. A pure function is like a math equation. 2 plus 2 is always 4. It doesn't change the outside world, and the outside world doesn't change it.
But software has to interact with the messy outside world. It has to print to screens, read files, talk to databases.
Right, and those actions are wildly unpredictable.
Yeah, like a hard drive might be full or a
Yeah.
network might go down.
Exactly. So Haskell isolates those messy, unpredictable interactions inside the I/O monad. It acts as a Merlock. The compiler knows that anything happening inside the I/O monad has side effects.
Oh, I see.
So what Aang did was create a custom container, the app monad, which wraps around that I/O airlock, but adds a whole new layer of context, which is the configuration environment.
Oh, wow. So the app monad is essentially a custom environment that says, I am a container that safely handles real-world input and output, and I hold all the configuration data, like the handle and verbosity.
Precisely. And because the printContent function is now running inside that app monad context, it doesn't need those settings passed to it as arguments anymore. The environment is just surrounding it.
It's just floating in it. Aang actually shows the code for how the function grabs this data. Instead of taking it as an argument, Aang uses a function called asks.
Right.
The syntax is v equals asks verbosity dot in args and h equals asks in vhandle. And then to actually print the output, Ang uses a command called lift.io.
Let's look at the mechanics of those commands. The asks function is basically the mechanism for querying the container.
Okay.
Instead of asking the function above it for the verbosity setting, printContent uses asks to query the app environment directly. It basically says, look into the environment arguments, find the verbosity setting, and assign it to the variable v.
So it literally reaches straight into the walls of the room to get what it needs.
That's so cool. And what about lift.io?
Remember that airlock we talked about?
Because the app monad is a custom wrapper built around the standard IO monad, you have to explicitly tell the compiler when you want an action to pass through the wrapper and actually interact with the real world.
Oh, so lift.io takes the print command and lifts it from the inner IO layer up through the app context so it can actually execute.
Exactly. Ang calls this entire architectural setup the ReaderT pattern, where variables are passed implicitly behind the scenes.
The ReaderT pattern, it's a brilliant way to clean up the code, but I have to play devil's advocate here for a second.
Go for it.
If you just look at the new signature, pandic to app, it doesn't tell you that the function requires a handle or a verbosity setting. It's hiding those dependencies behind the scenes.
Right.
Doesn't that make the code much harder to read and maintain for a new developer? I mean, it feels like the variables were just materializing out of thin air.
That is probably the most common and honestly the most valid critique of implicit dependency injection.
Because it feels a little like magic.
Yeah, exactly. And magic in software engineering is usually bad because it obscures the logic. But the mechanics of the ReaderT pattern prevent it from being opaque magic.
Wait, how so? Because from the outside looking at the function, I don't see those variables.
You don't see them in the specific function signature, sure, but the type system enforces them at the top level.
What do you mean?
When the application starts up, it must define the environment. It gathers the verbosity, the handle, and any other arguments, and it deliberately constructs that app monad container right at the start.
Oh, I see.
So from that point down, any function that returns an app action is mathematically guaranteed by the language to have access to that specific environment. It's not pulling from thin air. It's pulling from a rigorously defined overarching contract.
Okay, so it's not that the dependencies are hidden, it's that they are elevated to the level of the environment itself.
Exactly.
But, I mean, that elevation brings up a massive red flag.
It does.
If we've put these variables into an environment that surrounds the entire application, and any function inside the app monad can query them, isn't that just a global variable?
Yep.
Ang actually anticipates this exact critique in the journal, asking point blank, isn't this like a global config shared between numerous modules?
And Ang answers, in a way, yes, which is a deeply provocative thing to write.
Because in computer science, global variables are basically considered a catastrophic anti-pattern.
Oh, yeah. They are widely hated.
Let's unpack exactly why global variables have that awful reputation. The logic goes that if you have a variable accessible from anywhere in the program, any part of the program can accidentally change it, right?
Yes. It's the problem of mutable state. Mutable meaning changeable.
Right.
State management is arguably the most difficult aspect of software engineering. If you have a global configuration setting, say, a variable that dictates the access level of a user, and 50 different functions are all running concurrently, reading and writing to that global variable at the exact same time,
You create a huge mess.
you create what's called a race condition.
It's like having a single massive whiteboard in the center of the office. Everyone is trying to read the project deadline off the whiteboard, but anyone walking by with a marker can just erase the date and write a new one.
Exactly. It creates total unpredictability.
Because one function might read the verbosity as high, but a microsecond later, another function overwrites it to low, and suddenly your entire logging system just breaks down completely.
And that unpredictable state leads to spooky action at a distance, where a change in module A crashes module Z, and you have absolutely no idea why.
So when Ang says this acts like a global config, alarm bells should be ringing loudly.
They should. But Ang includes a crucial caveat. Yes, it is globally accessible within the context, but UT, it is a type-safe, read-only equivalent.
Wait, read only.
Yes. There is no mutation, and therefore no unwanted side effects.
So going back to the whiteboard analogy, everybody in the building can look at the data on the board, but nobody is allowed to hold a marker.
Exactly. That asks function we discussed earlier. It only reads, it cannot write. The Haskell language physically prevents a developer from altering the environment once it is set.
That is wild.
And the mechanics of the ReaderT pattern go even further to ensure absolute isolation. Ang notes that the environment passed to the calling function represents a specific, isolated configuration snapshot.
A snapshot. So if a function spawns a new process or calls a different part of the system, it doesn't just share the live whiteboard.
Right. If you need to run a subprocess with slightly different settings, say, you want to temporarily turn the verbosity up to maximum for just one specific heavy calculation, you don't alter the global environment.
What do you do instead?
You use a function that takes the current environment, creates a brand new modified snapshot, and passes that new isolated snapshot into the subprocess.
Oh, wow. So the original environment remains completely untouched.
Completely untouched.
Yeah.
This mechanism guarantees what Ang calls immutability by default.
Which is huge.
It's the bedrock of functional programming. When a system's context cannot change unexpectedly underneath you, you can reason about your architecture with absolute confidence.
So Ang managed to get all the convenience of a global variable, eliminating the need to pass arguments manually through the bucket brigade with absolutely none of the danger. The state is rigorously controlled.
Exactly. It's an elegant solution.
That distinction between messy, mutable global state and isolated, immutable context is really profound. And to help ground this abstract Haskell concept, Ang actually bridges the gap by comparing it to how a very popular, widely used language handles the exact same problem.
Python.
Right, Python.
It is a great pragmatic comparison. Python is the language of modern data science, web development, AI. It is incredibly flexible, but it faces the exact same issues with passing configuration data.
Ang points out that this Haskell refactoring is functionally equivalent to Python's scoped context blocks, specifically a feature called context vars.
Yeah.
Ang gives the real-world example of managing a database session. In Python, instead of passing the active database connection into every single function call, you can create a scoped block.
Right. Python built context vars to solve the exact same bucket brigade problem. It allows developers to hide that database session in a contextual background for a specific block of code, just like the app monad does.
So any function running inside that scope can implicitly access the database session without needing it in the function signature.
Exactly. It's conceptually very similar.
But then Ang highlights one massive structural difference between the two ecosystems. Ang writes, the only difference is in Haskell. This is compile time instead of runtime in Python.
And that is a world of difference.
We really need to define these two concepts because they represent two entirely different philosophies of software engineering. So what is the mechanical difference between compile time and runtime?
Well, the difference really comes down to when the program's logic is verified. Think of a compiler as a highly rigorous mathematical safety inspector. In a language like Haskell, before the program is ever allowed to launch, the compiler reads the entire source code.
It checks everything.
Everything. It checks every single type signature. It proves mathematically that if function J asks the environment for a verbosity setting, that setting will absolutely exist and be of the correct type.
No.
This exhaustive inspection phase is compile time.
Okay, and runtime.
Runtime is when the program is actually turned on, live, and executing its instructions. Python is an interpreted language. It is dynamically typed. It doesn't have that strict mathematical inspection phase before launch.
It just goes.
Yeah, it just starts running the code line by line.
So to put this in concrete terms, let's say I have a function that asks the context for a database connection, but due to, I don't know, a typo or a logic error, the context actually contains a simple string of text instead. What happens in Python?
In Python, the program launches perfectly fine. It runs for hours processing data. But the millisecond the execution hits that specific line of code and tries to use a string of text as a database connection, it fails.
It just crashes.
It crashes completely. It realizes the error at runtime.
Which means your users are the ones finding your bugs for you, live in production.
Exactly.
Okay, let me test my understanding here. Is compile time like a safety inspector checking the roller coaster before anyone gets on the ride? While Python's runtime approach is basically hoping the seatbelt holds during the loop.
That is an amazing analogy. Yes, exactly. Python prioritizes developer speed and flexibility, which is why it is so overwhelmingly popular. You can write and test code incredibly fast without fighting a strict compiler.
But that flexibility obviously comes at the cost of runtime danger.
It does.
And in Haskell.
In Haskell, that typo would never make it to production. The compiler would analyze the app monad, See that the function expects a database connection, but the environment is providing a string, and it would halt the compilation process immediately.
It just refuses to build the software.
Yep.
So the safety inspector just refuses to let anyone on the ride until every piece of track is mathematically proven to connect.
That is the power of compile time checking combined with the ReaderT pattern. The Haskell compiler rigorously checks those implicit dependencies before the software is ever deployed.
Wow.
It proves that every function asking for a variable will receive exactly what it needs and that no one is trying to mutate a read-only snapshot.
It completely shifts the burden of catching errors from the user at runtime back to the machine at compile time.
Exactly. It gives developers an immense, almost structural level of confidence.
It really is a fundamentally different way of thinking about stability. So we started this deep dive looking at a microscopic developer journal entry from August 2026, analyzing a little function called printContent.
And we used it to unpack the core mechanics of how complex systems handle state and context.
We saw how a system evolves from a cluttered, tightly coupled manual process, the whole bucket brigade thing, to a sleek, implicit dependency injection using a custom app monad.
Right.
We explored how immutability and read-only snapshots solve the terrifying dangers of global variables. And we saw the profound architectural difference between catching errors live at runtime in Python versus proving them mathematically at compile time in Haskell.
The overarching lesson here is that as systems scale, how you manage your context dictates whether your system thrives or just collapses.
And that is exactly why this matters, even if you never write a single line of Haskell. Understanding how to cleanly isolate and manage context is an architectural superpower.
It really is.
It applies to how you structure corporate departments, how you manage data pipelines, and how you organize any massive workflow. But before we wrap up, I want to leave you with a final lingering question to ponder on your own.
Well, let's hear it.
It builds directly on what Aang is doing here. We've spent this entire deep dive discussing how developers perfect deeply isolated, immutable, read-only context envelopes to prevent side effects and data corruption in software, right?
Yes.
And we know how powerful the app monad is for isolating state. So consider this. Could this exact architectural philosophy be the key to solving the massive data leakage and privacy issues we are seeing in modern AI development?
Oh, taking the concept of the ReaderT pattern and applying it to machine learning.
Think about it. Right now, large language models struggle with context windows. They accidentally bleed personal data from one session into another, or they ingest sensitive prompts and, regurgitate them later to other users.
Which is a huge security flaw.
Right. So what if an AI's memory and access to our personal data was strictly managed exactly like Haskell's implicit environments? What if every single prompt was wrapped in a read-only, perfectly isolated snapshot, mathematically proven by a compiler to be tamper-proof and strictly temporary?
That's a profound thought. It suggests a future where AI privacy isn't just governed by, a corporate policy, but is physically enforced by the architecture of the system itself.
Exactly.
Yeah.
Imagine an AI system where context leakage is rendered physically impossible by the container it runs in. It definitely gives you something to think about.
It really does.
When systems get overwhelming and the diagnostic waters get muddy, the answer isn't always to add more checkpoints or pass more variables down the chain. Sometimes you just have to fundamentally rethink the container. Thank you so much for joining us on this deep dive.
It was a pleasure unpacking this with you.